Okay, so today we are going to see the domains and ranges of our trigonometric functions. Let's recall how we define these functions. Now we know what their general definitions are. Let us recall those definitions. We first of all defined cosine and sine, and we did this with the help of the unit circle, whose center is taken at the origin of our coordinate system and whose radius of course is 1. That's why it's a unit circle. So if you are given some angle which corresponds to some rotation, either clockwise or anti-clockwise and by any amount, what we have to first do, we have to first put the angle in the standard position. What does that mean? It means that the initial line of the angle should coincide with the positive x-axis, and then the final line will be how it will be, okay, depending on the angle. Now, no matter where the final line lies, either like this or in whatever position it lies, it will definitely intersect this unit circle at some point. For example, here, if our angle is this acute angle actually, and let me just, although it ultimately does not matter, but still, let me just also indicate the fact that the rotation to which it corresponds is anti-clockwise. Okay, so this arrowhead for the rotation. Now this final line intersects the circle at this point, and that point will have its own coordinates, x coordinate and y coordinate. That x coordinate is defined to be the cosine value of that angle x, and the y coordinate is defined to be the sine value. That's the meaning of cos x and sin x. Then in terms of these two, we can define the other four trigonometric functions. Now you can see that these are functions taking on values, that is, once you give an input x to any of these functions, it's going to give you a value as an output. Now so naturally we can ask what the domains and ranges of these functions are. So let's next see this. Now obviously, because things start with cosine and sine, so it's natural to first of all do it for them. Now the definition of cosine and sine are such that there is no problem with taking just about any real number in place of x. You can take any x, and that will give you a cosine value and a sine value as output for that input x. And that is why the domains of the cosine and sine function are both the entire set of real numbers R. Okay, there is no problem in choosing any real number as input. That is why this itself is the domain. But that's just pretty easy. It's almost like doing nothing. Okay, you immediately get the fact that this is the domain of both cosine and sine. But what about the ranges of these functions? Let's think about the ranges. What does range mean for a function? Say you are given a function. What does the range of f mean? It means it's just simply the set of all outputs for the function f. So here also we have to think of the outputs. What are the outputs? You see, the outputs actually are nothing but the coordinates of the points lying on this circle. For simplicity, let us not think of both the functions at once. Let us first of all think of only cos x. What are the values of cos x? The values of cos x by this definition are nothing but the x coordinates of these points on the circle, and because the final line of our angle can be in any position, so you can imagine that for some angle every point is going to be the point of intersection of the final line of that angle. Or in other words, let me put it more in a more straightforward manner. Say I choose any arbitrary point here on the circle, anywhere, say here. Does there exist an angle whose final line will pass through this point if it is put in the standard position? Yeah, of course. That angle will have its final line looking like that. In fact, there will be many angles. Okay, one of them is this, another one will rotate one full rotation, and then it will rotate by that amount. So infinitely, in fact, many angles like that will be there. And that is why you will have the x coordinates of any point on the circle as your cos value for some x. And these x coordinates are going to be forming the range of the cosine function. Now think of the x coordinates. You have all the points on the circle. What are the x coordinates? How large and how small can the x coordinates of points on the circle be? Say you start your journey here at the point 1, 0. I said journey because now we are going to move the point on the circle to see what its x coordinates can possibly be. Now we choose any one of the two senses. Say I choose the anti-clockwise sense for rotating the point on the circle. In this specific position, its x coordinate is 1. Okay, and that is why in fact we have cos 0 equal to 1. So 1 is a range value. Range value means it's an element of the range because 1 is an output. Now if we start moving this point, say the point has come here itself, say in that figure, then what is the x coordinate of that point? For that you have to drop a perpendicular from that point on the x-axis, right? And that perpendicular will have its foot somewhere on the x-axis. The real number that corresponds to that point on the x-axis is the x coordinate of that point from coordinate geometry. Say this value is something, say x prime. Then x prime is just like 1, x prime is another output. But where is x prime lying? Note that x prime is greater than 0 but less than 1. Now you can imagine that as you move this point on the circle, the perpendicular will get closer and closer to the y-axis. And when the point reaches its highest position, the perpendicular becomes the y-axis itself. So the foot of the perpendicular, because we are drawing it on the x-axis, will be the origin. In that case, the x coordinate, or I mean I should not say the x coordinate, but the point which, or the real number to which this point corresponds is 0. Right. Just like this one is x prime, this one is 0. But if you do not stop here and continue your journey further on that side, then the foot will move to the left, foot of the perpendicular. So now it will have some other values, say x double prime. Now x double prime is negative. How far to the left can it go? It can go this far. For that point, for that point also, you can drop a perpendicular from that point to the x-axis, which will have length 0, and its foot of the perpendicular will be this point itself, and its coordinates are -1, 0. So the value of x that corresponds to this point is -1. But if you do not even stop here and continue your journey downwards, now again, the moment you cross this point and say you have come here, you can still drop perpendiculars from those points below the x-axis to the x-axis. They will also have their own feet. Again that foot will start moving towards the right. So it's like as the point moves along the circle, the foot of the perpendicular first goes towards the origin, reaches this leftmost point, and then again goes back, and it continues this back and forth motion. And in doing so, whatever x values it takes, those are precisely the elements of the range, and that means that the range is the closed interval -1, 1. Right? So we can write after this analysis the range of the cosine function. Let me write like that because I am writing in words. Is the interval -1, 1. We are taking closed interval because both 1 as well as -1 appear as values for the cosine function. So it's closed interval. The endpoints are also included. What about the sine function? What about its range? Now, if you think about the range of the sine function, this on the other hand is the y coordinate of that point. And to see what the y coordinate is, this time you have to drop a perpendicular from the point on the y axis, and that perpendicular will have its foot on the y-axis, if you want to call it the foot of the perpendicular, this point. So you can understand that whatever now you are going to do with sin x, we already did the similar thing with cos x. The only thing is that at that time the foot of the perpendicular was doing this motion on the x-axis. This time, however, this point will do that similar motion on the y-axis, because this highest point has coordinates 0, 1, and the lowest point has coordinates 0, -1. So this real number, or the real number to which this point corresponds, that lies between -1 and 1, just like this one. And that is why, by a similar argument, similarly, the range of the sine function is also same, closed interval -1, 1. That means they both have the same domain and the same range, but still they are not the same function, however. That we already know. Okay. So having seen the domain and range of these functions, let us now also see the graphs of these functions. So in order to draw the graphs, actually I won't draw the graphs of cos and sine first. With the graph of cos, I am also simultaneously going to draw the graph of the secant function sec x. There is a reason for that. But let us first see the graph of the cosine function. I kind of need this figure, so I am keeping it. Let me do it on that side. All right. Now, let me just draw the x-axis somewhere in the middle because I need some space above as well as below. Also, I will need this length. Want to make it as clear as possible. We are, of course, you understand one thing, that we are not going to form some kind of table of values and then plot those points. No, we are not going to do that. We are going to see the general shape of the graph and some special points through which the graph passes. And this is our somewhat long y-axis. All right. Now here's the thing. There are some, whenever you think of trigonometric functions, multiples of pi are, they hold some significance. Okay, at this point special things happen. So that's why on the x-axis we are going to locate these multiples of pi, sub-multiples also. First of all, the origin of course is 0. Then let me choose some length, say this much. Say this is pi over 2. Then pi. 3 pi over 2. 2 pi. It's going to be a little tight, but I will try to do my best to not make it messy. Similarly, on the other side, we have the negative versions of these things. Minus pi minus 3 pi over 2 minus 2 pi. Another advice, although this is not something that is standard, okay, I am just simply saying for your own sake, for your own understanding, if you want to draw a graph like this, then on the negative side, when you plot these points, and you are going to name them, because you will have to write minus. So it becomes a little messy if you write them in a single line. For example, we did this here, okay, because here we had plus and we do not have to write the plus sign. Here on the other hand, because of this minus signs, you need extra space. So if you do not have enough space, you write like this, okay, so that they become, they do not look messy. All right. Now, without regarding scales on the axis, and by scale what I mean, say this much on the x-axis is pi over 2. I am not going to consider that same length on the y-axis to also be pi over 2. I am just conveniently assuming some length to be 1, yeah, and this is where I need to be somewhat careful. For some reason, I want some space above 1 also. We will see why. Say this much is 1, then below the x-axis also this much is 1. You will put minus 1 here. So let me write 1 here and minus 1 here. Okay. And now I am going to draw two horizontal dashed lines through these points, 1 and minus 1. Because these lines will keep the graph of cos x within them. Why? That's because you know, you have found just now that the range of cos x is the closed interval minus 1 comma 1. So you know that the cos x values cannot go below minus 1, also they cannot go above 1, and that is why the graph will lie within this strip determined by these two dashed lines. Whatever happens to the graph of cos x, that is going to happen in this region only. Okay, it won't go above, it won't go below. Alright. Now, if one really goes, see, in order to draw the graph of cos x, we actually really need to know the values. Otherwise, how can you draw the graph? But if one really does go through the values, plot the points and does everything like what we do when drawing graphs, the graph will look like this. It will, you see, at least we know some things in the beginning itself. For example, cos 0 is 1. So when your x is 0, y should be 1. Cos pi over 2 is 0. So this is another point on the graph. At cos pi, the value is minus 1. This is another point. At odd multiples of pi over 2, cosine is 0, we already know. So at 3 pi over 2, it is again 0. At 2 pi, it is again 1. So the graph will be a wave like this. Right. You can imagine that it has become a little wobbly here, but it will be a nice wave. Roughly the shape will look like this. And a similar thing will happen to the left of the y-axis, like this. At minus pi over 2, for example, it will again become 0. So it starts to drop, reaches 0 at minus pi over 2. At minus pi, it will become minus 1. Okay. And at minus 3 pi over 2, this is another odd multiple of pi over 2. It's minus, but still an odd multiple, so it will become 0 here again. And at 2 pi, it will again become 1. Okay. It needs to reach this. And it will continue like that indefinitely on that side, on this side. So that is the graph of y equal to cos x. Now let us think of the function secant x. Note that we haven't yet said anything about the domain or range of secant x. Now we are going to do. Say you now think of the function secant x. By definition, this is just the reciprocal of cos x. And because we are taking reciprocal, we need to make sure, you already know, we need to make sure that cos x doesn't become 0. And that is why we have to avoid these points. The odd multiples of pi, this one, this one, this one, this one, the odd multiples of pi over 2 should be avoided while thinking of secant x. And that is why here x needs to be not equal to, x can be any real number but not this type of numbers where n is any integer. And this immediately tells us about the domain of secant x. So the domain is the set of real numbers, recall your set theory, set difference, from which the set of these real numbers is being removed. You can take any x as input but not these. This is the domain of secant x. And actually, because not just secant x but cot x also involves cosine in the denominator. Sorry, what am I saying? No, sorry, not cot x. I said the exact opposite thing. Sin x has, tan x, something is happening to me. I am saying things that I don't want to say. Instead of saying, let me just write. Tan x has cosine in the denominator. So for tan x also, this is the domain. Do you see that? There is no problem with the numerator. In the numerator you have sin x and you can put any real number in place of x. Sin x will give you a value. That's because there is no problem with the numerator being 0. The numerator can be 0 but the denominator cannot be 0. And that is why this same condition applies to tan x as well. And which is why tan x also has this domain. So secant x and tan x have the same domain and this is the domain. Because they are the same, so I am just talking about tan x also here. Ranges are however different, okay. We are not talking about tan x right now. So this is the domain of secant x. Now if I want to draw the graph of secant x, that means I will have to avoid these odd multiples of pi over 2. To do that, to see that I am really avoiding these things, what I do is I am going to draw dashed lines which are vertical and that they pass through these points. Okay, so this one passes through pi over 2. Another one passes through 3 pi over 2. On that side, you have this one, which passes through minus pi over 2. When talking about trigonometric functions now, for some reason I don't know why, diagrams, figures eventually get messy, but still you have to make them as nice as possible so that you don't get confused. See, already whatever we have drawn looks quite complicated, but if we do things like one thing at a time, then it's okay. We need not worry about this part now. You will realize why. So because the domain avoids these points, so we have kind of formed some barriers for us so that we can avoid these points by drawing these vertical dashed lines through them. Now let's think about the range of secant x. And in this, the values of cos x actually are going to help us, because after all their reciprocals only give us the values of secant x, right? Nothing else. And that is why somehow the range of cos x itself is involved in finding out the range of secant x. So I have to do it here itself. So we can now erase this part. Understanding that those odd multiples of pi over 2 are being avoided. Okay. With that understanding, let us now think of cos x. We already know that the values of cos x lie between -1 and 1. So you have these inequalities. Okay. Now we see not just this, but simultaneously we are also avoiding those x's for which cos x will become 0. And that is why actually we are considering two situations here. Either our cos x values are negative and like this, or positive and like this. Now say we think of these inequalities first. Okay, we are taking such x for which cos x values are negative and of course will be greater than or equal to -1 always. So you are now looking at two negative numbers here. One of them is -1 and one of them is cos x. What will happen if you take reciprocal? What will happen to the inequality? And this is where we need to recall a rule that we know from the basic rules of inequalities. Say you have two real numbers R1 and R2. Because we have this kind of inequality, not the strict one, so let us accordingly take this. Say both R1 and R2 are positive or both are negative. Both positive or both negative. Okay, this condition is very important. In that situation, if you take reciprocal, the inequality gets reversed. That is, you get 1 over R1 less than or equal to 1 over R2. Okay. However, if they have different signs, say one of them is positive and the other one is negative, obviously this has to be negative and this has to be positive, because a negative number cannot be greater than or equal to a positive number. For such a situation, if you take reciprocal, then inequality doesn't get reversed. That case, however, occurs rarely, in which we need to take reciprocal, and that's definitely not the case here, because here both the numbers are negative. Fine. That means if we take reciprocal, the inequality will get reversed. Now, if you take the reciprocal of -1, you are going to get again -1. The reciprocal of cos x is secant x. So you have secant x. The inequality was like this, now it will be like this. That is, for this type of cos x values, the secant x values are going to be less than or equal to -1. So the points that you will get on the graph of secant x for those type of things will be less than or equal to -1, will lie below this dashed line. And that is why I wanted some room below as well as above. Now let us erase this cos x, this label. And the fun thing is that in the graph of cos x, you see some peaks and some valleys, right? Some mountains. For example, there is this mountain between -pi/2 and pi/2. But we are not really talking about mountains here, because we are right now looking at cos values that are negative. So we are talking about these valleys. Say this valley lying between pi/2 and 3pi/2. Now the corresponding secant x values need to be less than or equal to -1 for these cos values. The fun thing is that just like cos x gets reciprocated to give you secant x, this itself also kind of gets reciprocated or reflected about this line, and you get this as a part of the secant x graph. The valley has been reflected about its lowest point and has become this mountain which has no bottom. Okay, it goes on and on and on. There is nothing that bounds secant x from below. Accordingly, you get one part of the graph of secant x like this. Now, where does these vertical lines come? The vertical lines make sure that this mountain, that is this curve, doesn't touch these vertical lines. That's because at pi over 2, secant x has no value. At 3 pi over 2 also secant x has no value. So the values of secant x which lie in this region, they create this part of the curve, part of the graph, but that graphs, although the lower you go, this keeps getting closer and closer to this line without ever touching it. The same thing happens here also. The lower you go, this part of the curve gets closer and closer to this vertical line without ever touching it. Okay. That of course we cannot draw because eventually we will touch it. However, that's the case. So this is one part of the graph of secant x. Similarly, you can imagine that the same thing is going to happen to this valley. The corresponding part of the graph of secant x on this side is going to be this. So unlike the graph of cos x, which is in one piece, which is a connected graph, a connected figure, the graph of secant x is broken into several parts, infinitely many parts actually. Why infinitely many? That's because just like these two valleys, you will keep on getting valleys. All of them will be reflected and will give you parts of the secant x graph that lie below this line minus 1. Now if you carry out this same kind of argument for these inequalities, here on the other hand, for some x's, for example for these x's, these x's, these x's, the cos x values are positive. And that's why here cos x is positive and 1 of course is positive. Here if you take reciprocal, again by that rule, inequality gets reversed. And what do you get now? This is secant x. This reciprocal of 1 of course is 1. You had this type of inequality, now you will have this type of inequality. Secant x is greater than or equal to 1. Now a similar thing happens with the peaks also. The peaks get reflected and become valleys with infinite height. So this is another part of the graph of secant x that lies above the line y equal to 1. These parts lie below the line y equal to minus 1. You will have other upper valleys like this. That is the graph of secant x. It somehow relates to the graph of cos x very nicely like this. Now, does a similar thing happen with sin x and cosecant x? Oh, but before we go to those things, what can we say about the range of secant x then? Because we have said so much. Well, you can see the range. The range is the set of all y values. What are the y values of the points of this graph? There are many disconnected parts, but the y values of any point on the graph doesn't go above minus 1 if it is negative, and if it is positive doesn't go below 1. So from all these things we can write the range of secant x, and the range will be this. I think now I can erase this part. The range of the secant function is minus infinity comma minus 1 union 1 comma infinity. Note that minus 1 is also a value which is taken on by the secant function. In particular, secant pi is minus 1, and that is why closed on the side of minus 1. Similarly, 1 is also a value. For example, secant 0 is 1. So, closed on the side of 1 comma infinity. This is the range of the secant function. Unlike the cosine function whose values lie between minus 1 and 1, here on the other hand, either the values are less than or equal to minus 1 or greater than or equal to 1. And a similar thing happens with sine. So you can see the book and go through a discussion with yourself about sin x and cosecant x, and you will see, which I am not going to do, that the cosecant function also has this same range. Again, why should that be the case? That is because just like cos x, sin x also has its values lying between minus 1 and 1. However, the graphs will not be the same. That's because sin x becomes 0 at some other points, not at integral multiples of pi over, odd multiples of pi over 2, but at even multiples of pi over 2, or at just multiples of pi, integer multiples of pi. So I will just simply write this. The above is also the range of the cosecant function. However, what is the domain of the cosecant function? Cosecant function is the reciprocal of sine function. So we have to avoid the points at which sine becomes 0. That is these points I said just now, that the integer multiples of pi, and that is why the domain however is the set of real numbers from which the integer multiples of pi have been removed. Okay, that is the domain of the cosecant function. The range is this. Now I want you to draw the graph of the sine. It's already there in the book. Okay. Draw the graph of the sine function. You just see once what is there given in the book, and then you do it yourself once, not again and again, because there is nothing to do about this again and again. So you just do it once, you see if you are getting all the parts right, and this is kind of a homework you can have for yourself. Whatever I did here with secant and cos, you do that similar thing with sine and cosecant, or cosecant and sine, however you want to call it, say it. Now next comes tan and cot. These are the remaining functions. For tan and cot, I need to draw another. Let me just get rid of this. These things become messy in the sense that once you draw one such figure, no, you cannot erase parts of it, then use it for something else. You cannot do that unless it's in computer. And if you want to really see how the graphs really look, like real machine generated graphs, you can of course always visit this site. You just go on Google and type this Desmos graphing calculator, and you will see the site Desmos. That's the first search result. Visit that site, and there you will see that you can, there is a part where the graph will appear, and on the left side there is the part where you can type equations, inequalities. The moment you give one some input, say x square plus y square equal to 1, immediately the unit circle centered at the origin will appear on the other side. You can draw many things, okay. You can even draw points, lines, parabola, whatever you want. That site is really nice for studying this kind of things. But that doesn't mean that you become lazy and don't do any kind of drawing on your own, because in your exam, on your final exam, you may be asked to draw these things. So unless you do it once, at least you won't be able to draw it then, okay, in the exam hall. But anyway, now we come to the discussion of tan and cot. So what is the tangent function? The tangent function is, by definition, this. We have already seen the domain of tan. The domain of tan is the set of all real numbers from which we remove those real numbers at which cos becomes 0. That is the odd multiples of pi over 2. Now, what is the range of tan? It may be slightly difficult to argue like how we argued about the ranges of cosecant and secant for tan. But it turns out that the range is, so this is the domain. It turns out that the range is the set of real numbers itself. It's slightly difficult to figure out why, but if you start plotting points by actually calculating values, you will see why. Now let's come finally to the graph of tan. So I need to draw the graph. So there is no need for this anymore. Again, you will have to draw x-axis, y-axis, all those things. And you will again need to locate those points which somehow involve pi. Towards the end of our discussion today, I will repeat something which I said before, so that you get to see not just these things but what lies ahead, okay. Because this, of course, this school level trigonometry is not the end of trigonometry. It's not even the beginning, it's the beginning of the beginning. Say this is pi over 2, pi, 3 pi over 2, 2 pi. On this side we have minus pi over 2, minus pi, minus 3 pi over 2, minus 2 pi. If you feel slightly confused by this, although we will quickly get used to it, but still after pi over 2 you are suddenly having pi and then 3 pi over 2. At first it may seem like confusing, but if that's the case, then you just think everything in terms of pi over 2. This pi actually is 2 pi over 2. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, like that. In that pattern it's going. So maybe that will help if you don't get it the first time. Okay, so what are the values that we need to avoid? We need to avoid these values. So now you know what to do. You draw vertical lines through those points that you need to avoid, and these lines will help guide the graph, will help you to guide the graph. Then let me drop another one that passes through 3 pi over 2. And on this side, another one that passes through minus 3 pi over 2. Okay, and here again, just like the range, suddenly I am just simply saying that the range is R. Also, the shape of the graph cannot be so easily obtained simply from the definitions by argument alone. You really need to see the values and you have to draw the graph. Either you do it on paper on your own, or you see the machine generated graph. The graph of tan x, just like the graphs of secant x and cosecant x also that you will see, is not in one piece. This one is also disconnected, and there are infinitely many connected pieces, and the pieces look like this. The piece between minus pi over 2 and pi over 2, note that the graph cannot touch these two lines, because at neither pi over 2 nor minus pi over 2 does it have any value, does the function have any value, and the graph looks like this. It comes up from the negative side, crosses the origin because tan 0 is 0, that's why, and then it goes up towards the positive y-axis. Also, when it does so, it has already crossed the negative side of the x-axis and is now traveling in the positive side of the x-axis. And that same remark that I made about the graph of secant x can also be made here. As you go lower and lower, the graph becomes closer and closer to this line without ever touching it, ever. Similarly, on this side, on the positive side, this part of the graph also becomes closer and closer to this line, x equal to pi over 2, without ever touching it. And the other connected parts are just copies of this, like this. I am not able to draw very nicely, but you get the point. Okay, so there are infinitely many copies of this. And the graph of the cotangent function, cot x, is also similar but shifted and reflected. That is, instead of this type of wave, you have this type of wave you see in the book. And lastly, let us also at least say what the domain and range of cot x are, because that's the last one for us. That at least we can say from analysis. this time the domain needs to avoid those real numbers at which sin x will become 0. That means we need to avoid the integer multiples of pi. So the domain will be this. And the range is just like the range of tan x, that is, this also is the entire set of real numbers. Okay. Now I said that I will say something so that we have some idea of what lies ahead. I have already said this in the previous video, or I think in the video before that, I don't remember, that these definitions of trigonometric functions that we are looking at are geometric in nature. These definitions use the unit circle. Everything from geometry has been used. Elements from geometry have been used for these definitions. However, that is just one way of doing it. There are other better ways that do not use geometry of defining these same functions, which one finds when one goes beyond calculus into an area of mathematics that is known as real analysis. It is something, okay, no need to be too concerned about that right now. Just take it as an information that in that area there are other definitions of these functions. Ultimately, it turns out that these different definitions give you the same function, but those analytic definitions are much superior for many reasons. One of those reasons is that using those other definitions, which do not use geometry but some advanced calculus kind of thing, you can extend these functions, these trigonometric functions, to even have complex number inputs. For example, you will then be able to calculate things like this, sine of 1 plus I. If you already don't know about complex numbers, which is highly unlikely, I mean, it's almost 100% sure that you know about complex numbers, at least superficially. This also has its own meaning. Okay. And what is even more surprising is that these are not just simply some mathematical games, okay. These have real world applications. Applications in electrical engineering, applications in signal processing, and many other things. Even application to those parts of physics where you have subatomic particles. Just think about it. Okay, so I am going to stop my discussion here itself today. In the next video on these things, we will start solving problems. So that's just it for tonight. So see you in the next video, and our next video is going to be this coming Saturday. Okay, there is a long gap. I'm suffering from insomnia. I have already made one post about that. So I need some time to sleep. But anyway, see you in the next video. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.